All right, it's 5:30. Let's go get started. All right, good evening, everyone. How's everyone doing? Everyone have a good spring break? It was okay. It was okay, honestly. My cat got out about a week ago, and haven't been able to find her. So I'm a little bit of a zombie today because I've been up kind of late worrying about her. But but being back at work, kind of takes my mind out a bit. So ironically, so going to try my best to get through today. But it's good to see you all again. I think that's the main. Okay. All right. So the plan for today is we're going to continue where we left off last Wednesday. So that was about 10 days ago. So if you remember from last Wednesday, we were talking about the finite volume method. And so today we're actually going to apply it. And so we'll see how that actually works out in 1D with diffusion. We'll be doing all the kind of the 1D stuff today. And then hopefully we'll end today with looking at a code. Okay. All right. I think that's homework 5. So homework 5 was posted today. It'll be due next Wednesday, I believe. And so that's going to be all based on all this diffusion stuff. Okay. And so with homework 5 being due next week, our next midterm is actually coming up. So our next midterm, it's not going to be next week. It's going to be the week after that, week 13. It'll be based on homework 4 and homework 5. So it's a little bit less content than midterm 1, just because it's a little bit shortened, and I want to basically cut it off a little bit early just so that you guys have some more time for the final project. I forgot about that today. So Wednesday, remind me Wednesday, we'll talk about the final project, kind of discuss what that is and the requirements for that. Okay. But yeah, probably that's better to talk about on Wednesday. Okay. All right. So I think that's all my announcements. Are there any questions I can answer before we get started for today? Yeah. Yes. So yeah. So I meant to grade your guys' homework 4 over the spring break, but I didn't get a chance to. But I'll grade that tomorrow and post the solutions for that tomorrow. Yeah. Yeah. Thanks for reminding me. Okay, all right, so let's go ahead and get started. So the subject for today is diffusion with finite volumes. Okay. And so, just like I mentioned last Wednesday, we're for this kind of the second half of the class, we're basically going to be repeating or kind of retracing our steps a little bit in terms of how we approach this class so far, right? And so if you kind of look back of how we've tackled this class, the very beginning of the semester, we first introduced the idea of finite differences, right? And then we took that idea of finite differences, we applied it slowly to our governing equation. So first we did diffusion, then we did convection, then we did unsteadiness, okay? And then we kind of arrived at kind of where we are today. And so we're going to follow that exact same path with finite volumes. So finite volumes is kind of a parallel method to finite difference. It's different, and you'll see just based on how we apply things, it is quite different in terms of how we do stuff, but we can still use it to solve all the same problems. So just like we did. So just like finite differences, we're going to learn how to apply finite volumes first with diffusion, then convection, then unsteadiness. All right, so let me go ahead and since today we're just focusing on 1D, we'll do 2D on Wednesday. Let me write out the 1D diffusion equation. The 1D diffusion equation is we have minus K d dx of dp dx is equal to Q of x. Okay. So if you notice, I wrote this in kind of a weird way, right? And so we have d dx of d phi dx, right? So we're taking the x derivative of d phi dx. Okay. And so of course you can simplify this, and that's kind of what we did for finite differences. And so this entire quantity right here is nothing more than just d squared phi dx squared. So that's our familiar second order derivative that we've known for diffusion. It's just that I've kind of broken it up a little bit. And so you'll see soon why I did this, because remember the main difference here, or the main thing that's going to make finite volumes different than finite differences, is we're going to be integrating this equation. Okay. So that's the main, big difference that we're going to be dealing with finite volumes. Is everything with finite volumes is integration. Okay, and we use that integration, ironically, to come up with an algebraic expression. Okay. So we kind of discussed this last Wednesday too. So when you're talking about finite volumes, there is a couple more steps involved in finite differences. So for that reason, a lot of people, especially when you're talking about the final project, they tend to, veer more towards finite differences because there's a little bit less steps involved. And so you may think that, a lot of these extra steps is just extra work just for the sake of it. But if you remember on last Wednesday, because of these extra steps, finite volumes has a lot of very nice properties that finite differences doesn't have, particularly for these kinds of problems. So for thermal fluid type problems, finite volumes is really nice, which is why, for a lot of the CFD codes out there, or stuff like OpenFOAM, you'll see them use the finite volume method because it does have a lot of really nice properties. Okay, any questions on this so far? Okay. All right, and so just like we talked about in finite differences, let's take a moment just to remind ourselves what diffusion physically represents. Because this equation is more than just an equation, right? So we use this equation to actually model some kind of physical phenomenon. Okay? So physically, remember, diffusion represents kind of the passive spreading or the even spreading of a quantity over space. And so if you have a certain quantity, and so let's say that our quantity E, let's say that it starts in kind of a small cloud like this. So let's say that you have some kind of localized heating, right? And so you have like a laser beam, you point it at a sheet of metal, right? And so at first, the heating or the temperature might be very localized to a certain area. Okay? Eventually, through diffusion, right? Through diffusion, that temperature or that heating is going to spread evenly in all directions. And so what you're going to see is that that heat cloud, you can kind of say, will spread to something kind of more like this. And so the kind of the defining characteristic of this is that it's even, right? And so it spreads equally in all directions. And this characteristic of spreading equally in all directions, this was represented in its finite difference scheme. And so if you recall, our diffusion term, okay, so we had our second order derivative. In 1D, we ended up with a scheme that looked like this. Okay, so phi I plus 1 minus 2 phi I plus phi I minus 1 divided by delta x squared. Where if we draw kind of a number line on this, we could say that we had a weight or the coefficient in front of the phi I term is -2. And then on phi I plus 1, phi I minus 1, we had a 1 on each side, right? I'm just purely looking at the coefficients in front. I know there's a 1 over delta x squared on the bottom, but we're just ignoring that just for simplicity's sake. So the reason I'm bringing this up again, is that diffusion is still going to be diffusion, right? So at the end of the day, it doesn't matter kind of what method that we use to solve it. Diffusion should physically be the same thing, right? Whether we solve it with finite differences, whether we solve it with finite volumes, whether we solve it analytically, you can even solve this with finite elements if you really want to, right? No matter what, the physical process, the underlying mathematical equation is still the same. Okay. So when we discretize this with finite volumes, we should see something similar. Maybe not exactly in this form, but it should have the same kind of spirit of having kind of equal weights or equal spreading on kind of both sides. So I want you to keep an eye out for that, as we go about, applying the finite volume method. All right. Any questions on this so far? Okay. All right. So let's get started then. So let's see how we actually apply the finite volume. Diffusion equation. Finite. Okay. So let me write down the diffusion equation again. So we have a minus k d dx of dphi dx is equal to q of x. Okay. And just to remind ourselves too, we want to solve this on, we're going to solve this on a series of cells or a series of volumes. Okay. Let me try something different. So, usually in the notes, what I do is I represent a 1D finite volume with just a segmented line. But I think that can get a little bit confusing in terms of, comparing it to finite differences. So let me try this. Let's say we are solving it on something like this. Each cell here, I'm going to give it a number. Good. I ended up with 6. Okay. So we have a system here with 6 cells, and so we have 6 basically solutions that we need to obtain. Okay? And we want to solve this equation on each of these cells. So first, when we're kind of deriving the equation, so let's focus on just one cell at a time. So we're just going to focus on this cell at the beginning. Let me go ahead and kind of blow this one up just so that we can kind of see it in. Okay, so for this one cell here, let's say that the entire length of the cell, we'll call it just L. And so since we're in 1D, the only dimension that the cell is going to have is just length. And the positions of each of the endpoints are going to be called X underscore L for the left side and X underscore R for the right side. Okay? So this is position, side, cell, and this XR here is position, right side of cell. And this L by itself, this is the length of the cell. Okay. So these are all the important kind of geometrical qualities that we're going to be working with. Okay. Oh, one more, I'm sorry. One more. So I'm going to draw a data point right in the middle of the cell, and we'll call this XC. Okay? And so this XC here stands for the position of the centroid of the cell. We have XL, X little l, XC, and XR. Okay? And L by itself is just the length of the cell. Okay, so with all those in mind, let's bring back the equation. Okay, so we have minus k d dx of d phi dx is equal to q of x. So let's apply the finite volume method to this. Okay. So to apply the finite volume method to this equation, or even just to any equation, what we're going to do is we're going to integrate this equation across a single cell. Right, so I'm going to apply integration to both the left-hand side and the right-hand side. So we're going to integrate here. We're going to do an integral here. Okay. In particular, we're going to integrate from x little l to x little r, okay, because that's going to take us from the left-hand side of the cell to the right-hand side. Okay, we're going to do that on both sides. So the bounds of both integrals are going to be xl to xr. Okay. And our integration variable is x, and so we're going to integrate with respect to dx. Okay. So let's go ahead and carry out these integrals. And we're going to use some of the tricks that we learned last time. Okay, so we're not actually going to be doing any integration. We're just going to be applying integration tricks. Okay, so it's a little bit of a a disappointment, maybe some people might consider that. But we are going to be applying integration tricks to get this into a form that's more tenable. Okay, so the first trick we're going to do. So let's do on the left-hand side first. Okay. We should notice that we have a dx on the bottom here, okay, and a dx right here. And so these two are effectively going to cancel out. What we can also do too is that we can take this minus k because it's a constant and we can pop it out in front of the integral. Okay. And so on the left-hand side, what we have is minus k integral from xl xr of d phi dx. Okay. Where if you've never seen this notation before, when you have just kind of a d just by itself, this right here is what's called a perfect differential.
Professor, I have a question.
Is there a question from Zoom?
Yeah. Is the finite volumes, is it used to solve the same kind of problems that we've been doing a different way, or is it to solve different kind of problems?
Yeah, that's a good question. So we're solving the same problems. It's just we're doing it a different way. Yeah.
So this can be applied to all the stuff that we've been doing and vice versa?
Exactly.
Okay.
Yeah, we're gonna reintroduce things kind of slowly. So we're starting with diffusion. So that was kind of the first thing that we did with finite differences. And so we're doing that with finite volumes first as well. And then we're gonna reintroduce convection and then reintroduce unsteadiness, and you'll see, it's like a parallel method. Yeah. So getting a perfect differential on the left-hand side is actually really nice because what that's going to do is that it's going to basically cancel out the integration. Okay? And if you recall, this is basically the application of Green's theorem. Okay? We'll finish that up in a second. So let's go ahead and work on the right-hand side. Okay. And so on the right-hand side, here, we have the integral of q of x times dx. Okay. So q of x right now is we have no idea what that function is. Okay? that changes based on every problem, right? So that's our source term. So our source term can change every problem. And so, at this point, we can't actually take any integration here unless we apply a trick. Because we don't actually want to integrate. Okay? It's kind of an ironic thing. So when you do finite volumes, you apply all these integrals to this equation, but you don't actually want to integrate because no one really wants to perform integration. Okay? And so we're going to simplify this integral by using what's known as the trapezoidal rule. And so the trapezoidal rule, if you recall from last time, it was a long time ago, so I'll go ahead and remind you. Basically, when you have an integral like this, you can evaluate it very quickly by just evaluating the integrand at the centroid of your domain multiplied by the length. Okay, and so through the trapezoidal rule, this integral here just becomes q of xc. Okay. And so we're basically evaluating our source term at the centroid of our domain. Wait. So that's what the q of xc represents. And so you're going to take whatever your source function is and plug in x sub c. Okay? And then we're going to multiply it by big L. So big L here, that's the length of our cell. And so with that, the right-hand side is actually done. And so we've applied our trapezoidal rule and we've have something. It's something that's not an integral. So all that we're left with here is just going to be on the left-hand side. But let me pause here for questions. So are there any questions on this so far? Okay. Okay. So let's go ahead and evaluate the integral on the left. Okay. And so on the left-hand side here, we have a perfect differential. And so that's going to cancel out with the integral here. Okay. And so left-hand side, we have minus k. And all we're left with is the function d phi dx. Okay. But we need to evaluate this at our integration bounds. And so it's going to be evaluated at x sub L and x sub r. Okay. Or from x sub L to x sub r. Right-hand side is going to stay the same. So the right-hand side is still going to be q of xc times L. And so if we evaluate this, so imagine this is kind of the step after you performed your antiderivative on the integral. And so after that step, we're going to have minus k multiplied by d phi dx evaluated at x is equal to x sub r minus d phi dx evaluated at x is equal to x sub L. And all this is equal to q at xc times L. Where these two derivatives that we got out are pretty significant. Okay? And so this derivative right here, this is basically the derivative of phi. Okay, so the rate of change of phi evaluated at the left face of the cell. or excuse me, the right face. Okay, this is X sub R at the right face. It's right here is the rate of change. Okay. And so our next step in the finite volume method is to take these, I call them phase quantities. Okay. And so this is not going to be the only time we get these. And so we want to take these phase quantities and basically evaluate them in terms of the cell-centered values. Because when we're applying the finite volume method, remember what we're interested in is we want a value for the solution that is valid for an entire cell. Okay. And so it makes sense that, ultimately what we're solving for is we want to solve for the solution at the middles of each of the cells. Okay. And so let me go ahead and draw the domain again. This here is cell 1, this is cell 2, 3, 4, 5, 6. Okay. What we want are the solution values at the middles of the cell. So this would be like phi1, this would be phi2, phi3, phi4, phi5, phi6. Okay. Because the idea is that, if we solve for the solution value at the middles of the cell, that's going to be a value that's valid for that entire cell. Okay. But we don't have that right now. So what we have here are derivatives at the faces of a cell. Okay. And so once again, let me go ahead and take one cell here and we'll kind of blow it up here. And so if I call this, this is going to be a generic cell. And so I'll call this phi sub C. Okay, so that's C stands for kind of the center of the cell. Okay. What we currently have, our equation, is quantities that are evaluated here. Okay, so we have basically this is d phi dx. Put it down here. So this is basically d phi dx at x sub L in this case. This is d phi dx x sub R. Right. So when I say that, we want to represent these phase quantities in terms of the cell center quantities, I basically want to take these, okay, are two derivative expressions, so d phi dx, okay, and I want to represent them in terms of these quantities. Okay, so it's phi sub c. But of course, we can't do it with phi sub c alone, and so we need to get some neighbors involved as well. So we're going to have a neighboring cell on the right and a neighboring cell on the left. Okay. And they're each going to have their own cell-centered values as well. And so on the left-hand side, we're going to have phi sub big L, and phi sub big R. Okay. Sub big L and phi sub big R. So phi sub big L and phi sub big R, these are the cell-centered values for the neighboring cells on the left and the right. All right, so let's go ahead and do that. So let me write out both of our derivative expressions here, and then we'll see if there's a way we can put them in terms of, all the cell-centered values. Let's do d phi dx at x sub L. Okay. And we're going to have d phi dx x sub R. Okay. So we have derivative expressions here, and we want to represent them in terms of kind of the neighboring cell values. Okay. All right. So there's a couple ways that to kind of explain this. And so there is the kind of the finite volume way. The finite volume way kind of basically denies the existence of any other method. And so the finite volume way thinks that it's the best. And so it has its own way of describing things. But there's kind of an easier way to describe this. And so I think it's that utilizes something that we've done before. Okay. So let's bring back an old friend. I think once I kind of mention this, it should become kind of clear. It's just that the purists, the finite volume purists, don't like to call it this because it uses something else. But let's take these derivatives and let's represent them with a forward difference. A forward difference using the cell-centered values. Okay. So let's do the one on the left first. Okay. And so on the left, a forward difference on the left-hand side would be phi sub c minus phi sub L divided by the distance in between them. Okay. And for now, we're going to assume that we have a uniform grid. And so all of our cells are evenly spaced. And so the distance in between them is just going to be L. Okay. Or in other words, the length of the cell. So there is kind of one cell length in between phi sub c and phi sub big L. Okay. And we have the same thing on the right. So on the right, we have phi sub big R minus phi sub c, all divided by L. So I think, within the context of this class, that's kind of the easier way to describe it. So we're basically utilizing a little bit of finite differences inside our finite volumes. Okay. If you're curious about, the finite volume way to describe this, by applying this forward difference, what we're essentially assuming is we're assuming that the solution varies linearly between the cells. And so in other words, we assume basically a linear profile. Okay. And so if you assume that the solution varies linearly between each cell, then the slope of the solution is just basically the difference, it's just rise over run. So you take the difference between the two, the two solution values, and you divide by the distance in between, okay? Which is exactly the same as forward difference. And so, I think within the context of this class, if you think of it as just a forward difference, that makes it, I think, a little bit easier to kind of understand. Okay. Okay. So let's go ahead and put this all together. And so, we took that detour, but remember, what we're working with is essentially this equation up here. Okay. So let's put these expressions back in there. Let's simplify it a little bit, and then we're going to arrive at our final equation. Okay, so if we put it all together, on the left-hand side, we're going to have minus k. And inside here, we have our derivative terms. And so first we have phi sub r minus phi sub c divided by L minus phi sub c minus phi sub big L divided by little l. Okay. L's are looking like E's. There we go, it's better. Okay. And this is equal to our trapezoidal rule, q of x sub c times L. Okay. So let's simplify this. And so I'm going to divide both sides by minus k. Multiply both sides by L. And then from there, I'm going to combine a couple like terms on the left-hand side. Okay. And so if we do that, we end up with phi sub r minus 2 phi sub c minus phi sub L is equal to minus little l squared divided by k times q of x sub c. And if you want to put this in even more kind of familiar terms, the cell size L oftentimes you'll see that represented in terms of the grid space. Okay. So essentially the same thing. Question, yes. Yes. Yeah.
The first term is QR minus QC.
Yes. Yeah. Mm-hmm. Yeah, both QCs have to be negative. So the first one's QR minus QC. The second one was QC minus QL. They're both forward differences. Yeah. Right. So another form of this equation that you'll see. So instead of the cell length L, sometimes you'll also see this as just delta X right here. Okay. It's the same thing. So the grid spacing, just the distance in between the grid points, that's the same thing as the size of the cells. So kind of a minor kind of application. Okay. Right. So we have a finite volume equation here. So are there any questions on how we got here? All right, so you might be looking at this equation and you might be getting some crazy deja vu. And so that is intentional. Okay. And so, I'm going to scroll up for just a second. So if you look back to kind of where we started today, remember I've reminded you of, our finite difference days where we took the second order derivative and we just applied finite differences and we ended up with this 1 - 2 1 pattern, right? So we fast forward to today. We have the exact same thing, right? Oh, there should be a plus here. Sorry. Okay. Now it's the same thing. So we have a 1 - 2 1. Okay. With some stuff on the other side. All right. So you might be looking at this and you might be thinking, we just wasted the last 30 minutes of class, right? So we went through all this integration. We did all these kind of weird integration tricks. We end up with exactly the same thing as we did with finite differences, right? So we did in a way, but also not in the same way either. Okay. The big difference here is that, remember, this equation here, we're applying this at the cell centers. So that's going to have some minor and kind of some major differences in terms of how we apply it. Okay. On the minor side, you can see here that the source term QC or Q, okay, Q here is evaluated X sub C. And so just kind of on a smaller note, when you're evaluating the source terms, you want to make sure you're evaluating them at the cell centers. Because up to this point, when we have these functions, we evaluate them only at the grid points, okay, which is what we did with finite differences. And so you're going to have to shift that over just a little bit when you're doing finite volumes, because they have to be applied at the cell centers. So that's kind of the first thing. But the other big difference that it makes here is that because we're at the cell centers, it's going to change the way that we apply our boundary conditions. And unfortunately, it's going to make applying the boundary conditions a bit more difficult. Because now, the cell centers, those cell centers are not going to be on the boundaries. So unlike finite differences, where remember in finite differences, our boundary conditions became equations. Now what's going to happen is that our boundary conditions are going to modify this equation. So this is kind of the big sticking point between, in terms of applications, in terms of, whether people prefer finite volumes or finite differences. Okay? Some people like the fact that, in finite differences, when you have a boundary condition, you can count on that being its own equation. And it kind of becomes simple in that way. But some other people like the fact that, you have for finite volumes, you have one kind of base equation and you apply modifications to it to apply the boundary conditions. So it's a matter of taste. I would say that generally more people kind of lean more towards finite differences, partially just because that's the first thing most people learn, but it is kind of important to know. All right, so the next thing we're going to do today is we're going to learn how to apply boundary conditions to finite volumes. All right, any questions on this? Okay. And so just like, just like we had in, finite differences, we're gonna have two different types of boundary conditions here. We're gonna have Dirichlet boundary condition and Neumann boundary conditions. And so we're gonna go over both. Let's go through Dirichlet boundary conditions first. And so if you remember, a Dirichlet boundary condition is a direct specification of the solution value at the edge of the domain. And so visually it looks like this. Let me go ahead and draw our finite volume domain again. Don't need them here. The Dirichlet boundary condition is like saying that on this side, okay, on this edge of the cell here, and so Dirichlet boundary condition, so let's say we have it on the left-hand side of the domain, does that phi has to be equal to some pre-specified value phi naught. And so previously in finite differences, that equation right here, okay, this phi is equal to phi naught, that just directly became our equation. So we put that basically directly into our matrix. Okay. So there's really no work to really do. That became that. Okay. In finite volumes, okay. In finite volumes, we're going to get one equation for each cell of the domain. Okay. In finite volumes, what this Dirichlet boundary condition is going to do, it's going to modify the equation for cell 1. Okay, so let's see how that happens. So I'm gonna write out the finite volume equation, but I'm gonna go back a couple steps. Okay? I'm gonna go back to the step where we had our face derivatives. All right, and so if we go back a few steps, our finite volume equation looked like this. So we have minus k times d phi dx xr minus d phi dx at xl is equal to q at xc times delta x. All right, so let's go ahead and apply our next steps. So remember, our next steps is to apply our usual forward difference here. And so for x sub r, this d phi dx here is going to be x r minus x c all divided by delta x. Okay. And so for the left neighbor, for the right neighbor, this is fine because we're on the left-hand side of the domain here. Okay. And so if we're looking at cell 1, we have a neighbor on the right. And so our neighbor on the right here is going to be cell 2. Okay. All right, so that one's okay. For dpdx on the left face, we can't do this, right? So we don't have a left neighbor here. And so we can't use our usual expression. So we can't do phi sub c minus phi sub l divided by delta x, because there is no phi sub l, because it's nothingness. Right? We don't have a left neighbor, but what we do have is our Dirichlet boundary condition. Let me do this. So for cell 1 right here, for cell 1, we know that on the left-hand side here, we have phi is equal to phi naught. This right here is phi sub 1. This here is phi sub 2. Okay. We know the distance between phi sub 1 and phi sub 2 here is delta x, right? That means the distance between phi sub 1 and phi sub naught is going to be only half of that, right? So instead of traveling from the center of one cell to the center of another cell, we're traveling from the center of one cell to its edge. So this is just going to be delta x divided by 2. Okay. And so let's do our same forward difference, but let's use just these quantities right here. Okay. And so if we apply our usual central difference, or excuse me, forward difference, we have phi 1 minus the Dirichlet boundary condition phi naught, okay, divided by the distance between them, which is delta x over 2. Okay. And this is equal to dphi dx at x L. If we simplify this, since we have a divide by 2 in the denominator, we're going to bring that up top. So we have a 2 phi 1 minus 2 phi naught divided by delta x. Okay, so let's plug that in. And so if we plug that in, we get a minus k times phi sub r, which in this case, I'll just go ahead and plug in for that. So this would be phi 2 minus phi 1 divided by delta x, okay, minus 2 phi 1 minus 2 phi naught divided by delta x is equal to q at xc times delta x. Okay. Let's simplify this. So since phi sub naught is a Dirichlet boundary condition, that's something that we know. Okay? So let's go ahead and move that over to the right-hand side. Do the same thing I did before. So I'm going to divide by minus k and multiply by delta x. And so if we do all those things together, what we end up with is the following. So we have b2 minus 3 b1 is equal to minus delta x squared by k times q of xc plus minus, I'm sorry, so we have a minus 2q naught. Right, so this is our modified equation for the first cell that incorporates the Dirichlet boundary condition. All right, any questions on how we obtain that equation then? Okay. All right, so for this problem here, we went through the whole process, and so we went through the whole process of starting from the finite volume equation, and we saw how we actually applied the Dirichlet boundary condition. Okay? This particular example was for if the Dirichlet boundary condition was on the left. Okay. If the Dirichlet boundary condition was on the right, it's going to change the solution a little bit because it might change the signs, right? And so when you're first doing these, I would always recommend that you start from the finite volume equation and then work your way through it. Sometimes it doesn't make a difference. Sometimes it does make a difference. And so until you kind of really get the hang of it, it's good to kind of just go from scratch and do it from there. So just like finite difference. All right, so let's do the Neumann condition. All right, so for the Neumann condition, remember what this specifies is that this specifies the solution derivative at the boundary of the domain. All right, so for this example, let's say we have a Neumann boundary condition on the right. Let's say that we have a cell on the edge. So we have cell 6, we have cell 5, and then what the Neumann condition says is that d phi dx at this location is equal to some specified value we say again. Okay. So the nice thing about finite volumes is that we went through kind of this whole lengthy process for Dirichlet boundary conditions. Okay. Maybe up to this point, you thought of Dirichlet boundary conditions as the easier one, finite differences. Okay? For finite volumes, it's reversed. And so for finite volumes, the Neumann boundary condition is a little bit easier. Okay, so just like before, let's start with the finite volume, the general finite volume equation. And so starting from the finite volume equations, we have minus k dpdx at xr minus dpdx at x sub L is equal to Q sub Q at XC times delta X. Okay. Okay. And so we're going to apply this at cell 6. That's the one that borders the Neumann boundary condition. Okay. Let's start by looking at this term that I've circled. So this term that I've circled here is the solution derivative on the right face of the cell. That's the solution derivative at the right face of the cell. Let's look at our diagram up there. And so our Neumann boundary condition says that dpdx on the right face of cell 6 is equal to gamma. Okay. And so what a coincidence. And so, the Neumann boundary condition is an expression of the derivative. Okay. And in our equation here, we have the derivative evaluated at that exact same location. Okay. And so this is nice. And so for finite volumes, we can just plug in the Neumann condition directly into here. So I'm going to replace this entire expression here just by gamma. So we don't have to plug in, we don't have to do any forward difference, we don't have to do any of that stuff. We just plug in the Neumann boundary condition straight there. Okay. For the other one, we do have to plug in for this. So for this one, we're going to plug in our forward difference. We have phi 6 minus phi 5 divided by delta x. Okay. But for the other derivative, we don't have to worry about it really at all. Okay. All right, and so if we simplify this, we end up with a minus k times gamma minus phi 6 minus phi 5 divided by delta x is equal to q at xc times delta x. Okay. Let's go ahead and simplify this like we usually do. And so all the known quantities, I'm going to move to the right-hand side. I'm going to divide by minus k multiplied by delta x. And all we're left with is minus phi 6 plus phi 5 is equal to minus delta x squared divided by k times q of xc minus delta x times gamma. And so this equation right here is our finite volume equation for the cell that borders the Neumann boundary condition. This one you have to be particularly careful because if you'll notice here, this term here on the right is negative. Okay? That is directly correlated with the fact that this was a Neumann condition on the right. If our Neumann condition is on the left, the sign of this term here will change. And you'll see that in the example that I'll do, next here. All right, so we have about 5 minutes left. And so I think what I'll probably do is I'll probably start the example. We'll probably get up to the point when we apply boundary conditions, and then we'll finish up the example on. Before we jump into that, are there any questions on this? Okay, all right, so let's go ahead and do the example. All right, so let's consider the following equation. So our equation here is going to be 3 d squared phi dx squared equal to 2x squared. Okay, so that's our equation. We're going to solve this on the domain of 0 less than or equal to x, so that's equal to 1. Okay. We have the following boundary conditions. So on the left-hand side, we have a Neumann boundary condition. We have d phi dx at x is equal to 0. This is going to be equal to 0. And on the right, we have phi of 1 going to be equal to 10. Okay. All right. And for this particular problem, since we're going to be solving this one by hand, we're going to use a very coarse mesh. And so we're going to use a grid with 4 cells. Okay. And so our domain is going to look like this. So we have two, 3. We have cell 1, cell 2, cell 3, and cell 4. Okay. So the left-hand side here, we have d phi dx is equal to 0. And right here, we have phi is equal to 10. Okay. So that's our equation. All right. So first thing I want to do here is let's go ahead and write down all of our important variables and what their values are. Okay. So first let's specify what the value of k is. Okay. So if we look back at our equation here, we have 3 d squared phi dx squared is equal to 2x squared. Okay. And so for this particular problem, because normally we have a minus out in front, our k is equal to -3. Next, we have delta x. Delta x is the distance between each cell center, or in other words, another way you can say it is it's the length of each cell. Okay. Since we have 4 cells here, and the length of our entire domain is 1, our delta x here is going to be 1/4, or in other words, 0.25. All right. Last thing I want to do before we start writing down the equations is I want to write down the coordinates of each cell center. Okay, from x1, x2, x3, x4. Okay. Because now that's going to be relevant, because now that's going to be basically what we're going to use in our equation. Okay. Okay, so you have to be a little bit careful here, because you know the fact that we're using cell centers is a little bit tricky. Okay. So we know the distance between the edge of the domain and the edge of the first cell is 0.25, right? So that's the size of the cell. So if we're looking at the middle of that cell, okay, that means x1 here. The location of the center of cell 1 is going to be 0.125. Okay. Once you get kind of the first one, the others kind of fall very quickly off of that, because you just have to add the grid spacing to that. And so x2 here is going to be 0.125 plus 0.25. So that's going to be 0.375. X3 here is going to be 0.625. And x4 here is going to be 0.875. So that's going to be, so I think that's going to be the trickiest thing with applying finite volumes is this kind of getting into the mindset of thinking, you know, we're looking at the cell center now instead of the nodes in the grid. All right. So we didn't end up writing any equations, but that's okay. So I think, you know, we'll save that for next time. Any final questions on this before we wrap it up for today? Okay, all right, so that's all we got time for. So we'll pick this up on Wednesday. We'll talk about the final project on Wednesday as well. Okay. And so thank you guys for coming today. You know, I know first day after break's always a little bit tough, so I appreciate you guys coming out. If you haven't picked up your midterms yet, I brought them again today, so you guys can pick them up. I'll grade homework for us by tomorrow and post a solution so you have that then. But besides that, hope you guys have a good night, and I'll see you guys on Wednesday.
Dr. Tran.
See you guys. You too.
Dr. Tran. Dr. Tran.
Hey, what's up?
Hey, I saw your email just before class. Is it fine if I stop by on Wednesday?
Yeah, I'll be here Wednesday.
Alrighty, thank you.
Yeah, sorry I know you're looking for the solutions, but I'll post them up tomorrow. Just yeah, I just had a lot on my mind recently. So
Oh, no worries, I get it.
And then the coordinates. So on your graph, X 0, 0.